Alright, this video is on bond polarity and a little bit of a discussion in electronegativity and also partial charges. Okay, so what we're talking about is covalent bonding and this idea of sharing electrons. Okay, so what we haven't talked about yet is that the fact that not all atoms share electrons equally. Okay, so then that puts covalent bonds into two categories, and those two categories are called nonpolar covalent and polar covalent. So a nonpolar covalent bond is defined as a situation when electrons are shared equally or nearly equally, and that's something that we're going to get into in just a minute. So we're talking about, say for example, if we have an F2 molecule, right? And so it looks like this, single bond in, fluorine's diatomic molecule. So in this case, the question is, does either atom in this bond have a greater attraction for the electrons? And since they're both fluorine, the answer to that is no. They have an equal desire for the electrons, and so they share those two electrons in that single bond equally. Okay, so that's referred to as a nonpolar covalent bond because both the atoms have an equal desire for the electrons. Okay, so basically nonpolar covalent bonds are going to be your diatomics. And there are a couple other situations that we'll get into. Actually, there's mainly one other big one, but mainly we're talking about your diatomics. Okay, so F2 being a great example, but all your diatomic molecules exhibiting nonpolar covalent bonding, an equal attraction for electrons. So then, excuse me, that raises the question of, well, what if the attraction for the electrons is unequal? So of course that's not called a polar bond. I mean, that's not called nonpolar covalent. It's called a polar covalent. And in a polar covalent bond, we have an unequal sharing of electrons. Okay, and that's where one atom has a greater attraction for the electrons. So I guess maybe before we give an example of a polar covalent bond, let's jump down and discuss electronegativity, which we have discussed before. It's just a quick reminder. So electronegativity is defined as the ability of an atom in a molecule to attract electrons. And the electronegativity trend increases as you move up a group and increases as you move to the right, making fluorine your most electronegative atom. Of course, the noble gases are excluded from this discussion because if you think about it, they really have no desire for an electron in a molecule. So fluorine is your most electronegative, with francium being your least electronegative. Okay, and so that is what determines how much an atom wants the electrons. That's what determines their attraction for the electrons. It's all about electronegativity. So when we go back up to polar covalent, if we have a polar covalent bond or an unequal sharing of electrons, basically we're going to have two atoms with different electronegativity values. So if you want to add that, you can. That in a polar covalent, they're going to have fairly decent differences. Chester, please. In their electronegativity values, and that's what gives us an unequal sharing of the electrons. So a great example would be basically anything bonded to fluorine, because fluorine is your most electronegative atom. So, for example, HF is considered a polar covalent bond. Here, do you want to see my dog? Ready? Just look at my dog. There's Chester, and there's Ellie. See, this is what they do while I film your lecture videos. Okay, sorry. I thought you would like that detour. Whew, okay. So back to Chem. Oh, man. Chester. I don't know what we were discussing. Oh, okay, so an unequal sharing of electrons. So if we're talking about hydrogen and fluorine, okay, in this bond, right? Who has the greater attraction for the electrons? It's obviously fluorine, most electronegative atom. Fluorine wants the electrons more, making this bond a polar covalent or an unequal sharing of electrons. Okay, lots of other examples. Basically, we could go on forever. Water, of course, is polar covalent, talking about the electronegativity difference between the hydrogen and the oxygen. Okay, huge difference in electronegativity, huge unequal sharing of the electrons, thus making the bond polar. If you notice your table where I have just drawn your arrows, it might be a little bit hard to see, but it is, electronegativity values given to you in that table, okay, and they range from, I think the lowest is francium with 0.7, all the way up to fluorine, whose electronegativity is 4. Okay, and it's just a scale that they use to measure the attraction of electrons in a molecule. So while it's not super important, it's worth knowing that there is a scale for electronegativity values. If you look underneath, there's a chart, and I'll quickly summarize this chart. It's worth discussing, but it's not the biggest idea in this section. Okay, so the chart says the electronegativity difference, and then the bonding type, and then an example. Okay, so we'll fill in the example together. So the difference goes from 0 to 0.4, 0.4 up to 2, and then greater than 2. Oops, that would be this way, right? Greater than 2, sorry. Okay, and it tells you that this is a nonpolar bond, it tells you that this is a polar bond, and it tells you that this is an ionic bond. Okay, so we can use the periodic table with the electronegativity values as a little reference for this. So for example, if you look at, we'll go back to F2, okay, in our example, whoops. And if you look at fluorine's electronegativity value, it's 4 in the table, right? And if you look at the second fluorine's electronegativity value, it's also 4, of course, meaning the electronegativity difference between the two atoms is in fact 0, which falls into this nonpolar bond. So 4 minus 4 gives me 0. Okay, the other one that is worth drawing your attention to is a carbon-hydrogen bond. Okay, now I know that's not a real Lewis structure, okay, but like if this was CH4 and we're talking about the bond between the carbon and the hydrogen, if you do an electronegativity difference, if we look it up in our chart, okay, I'm talking about looking it up here, carbon is your more electronegative, it's 2.5, and hydrogen has a value of 2.1, which gives you an electronegativity value of 0.4, which actually lies on this border, okay? But for our purposes, and this is a huge takeaway, you might want to write this down somewhere in the margin of your paper, carbon-hydrogen bonds are considered nonpolar, okay? Because the electronegativity difference is small enough that really carbon doesn't really attract the electrons any more than hydrogen does, okay? So all carbon-hydrogen bonds are considered nonpolar. And we'll go over that in class. Okay, if we look at HF, for example, in our polar category, if we do an electronegativity difference, and we take the fluorine's value of 4 and the hydrogen's of 2.1, we get a value of 1.9, which of course falls into this range of 0.4 to 2, okay, being a polar covalent bond. And then they use a third category, which is pretty much common sense because we know ionic bonds are metals and nonmetals, but you can also look at electronegativity. So if we look at something like, KBr, okay, and we look at K's value, bromine's value is 2.8 and K's value is 2. We get K's value is 0.8. I apologize. My goodness. Okay, K's value is 0.8. We get an electronegativity difference of 2. That's where I was going with that, which then determines my bonding to be ionic. Okay, this is just a very simple way to classify types of bonds, but we can also do it based on kind of like a common sense discussion, okay, whether or not they're going to share equally or unequally, or of course whether or not they're going to be ionic. Okay, so there are 6 little practice at the bottom. It just says to classify the type of bonding, polar, nonpolar, or ionic. So if you want to go ahead and do that, and then I'll quickly give you your answers. You may want to hit the pause button. Okay, so H2 in number 1, of course, is nonpolar bond. In number 2, SO2, of course, is polar. Okay, S is more electronegative. Less electronegative, my goodness. O is more electronegative than S, thus resulting in a polar bond. In number 3, NO, N is less electronegative, O is more electronegative, resulting in a polar bond. In number 4, NaCl, of course, is ionic. In number 5, CSF, of course, is ionic. And number 6, the bond between carbon and oxygen is polar because oxygen wants the electrons more electronegative. Okay, so that's this discussion on polar and nonpolar in electronegativity values. we're going to go to the back of our paper, and we have just one section left, which is partial charges. All right. So your heading is partial charges in polar molecules. Okay, so if we, oh, sorry, you can see all my notes here. If we talk about HF, for example, hydrofluoric acid, if we look at a Lewis structure, of course, the Lewis structure looks like this, and we've already determined today that this bond is a polar bond, okay, because F is more electronegative and wants the electrons more. What we haven't discussed, though, is because F is more electronegative, what that means is that F draws the electrons toward itself more of the time, okay, because fluorine pulls the electrons toward itself more of the time, it acquires a partial charge. Now, a partial charge is not a full charge, it's a partial charge, okay? But because fluorine holds on to the electrons more, fluorine acquires a partial negative. And that's shown in a picture by the lowercase delta, the Greek letter. Okay, you guys know uppercase delta is a triangle. Well, lowercase Greek letter is kind of like a cursive S looking symbol, okay? I'll do it one more time. It looks like a like an S, and then you kind of cross it, okay? That's a lowercase delta, and it means partial. So if you want to write that, you can. It just means a partial. And because fluorine is more electronegative and draws the electrons toward itself more of the time, it acquires a partial negative. Why negative? Because electrons are negative, okay? So then if fluorine has a partial negative, well then hydrogen is having the electrons less of the time, which means it's going to acquire a partial positive. So the same thing, that little partial sign with a positive, okay? We can look at a different molecule as well. So if we want to look at, let's do CO2. Okay, CO2 has two double bonds. So there's CO2's molecule. If we think about the bond between the carbon and the oxygen, O is more electronegative, meaning this O is going to draw electrons toward it, partial negative. This O is going to draw electrons toward it, partial negative, while the carbon has them less of the time, partial positive. Okay, so that's one way to do partial charges. There's a second way to do partial charges. So I want to show you that now. The second way is to do it with an arrow, okay? And the arrow points in the direction of the more electronegative atom. So in this case, it would point toward the fluorine, okay? It's like drawn parallel to the bond. Points like this, and then you cross it at this end. I think as a way to show you that kind of looks like a plus sign, right? So that this is your partial positive and this is your partial negative. You could do it on CO2 also, but on CO2 you would draw two arrows because you have two bonds. Okay, so one arrow for this bond, and it would point towards your oxygen, more electronegative, and you would cross it here. And then your second arrow pointing toward this oxygen, and you would cross it here. So both those ways, okay, the lowercase deltas or the arrow are two ways to designate partial charges. You don't have to do both on a molecule, like this is kind of overkill, but it's very important to be able to recognize that they mean the same thing.